So in this second video of section 11.1, we're going to revisit the M&M example a little bit and use it to help us determine how to calculate the p-value from the test statistic. We'll also talk about conditions necessary and the proper way of writing a null and alternative hypothesis. All right, so we look again at the M&M example. We had certain percentages that we thought the different colors would be based on information from the Mars Corporation, the people that make M&Ms. And so we were looking at the counts from our sample that I took from the bag of 60 M&Ms. And we could look at the individual p-hat values. So for example, the p-hat for the blue was 7 out of 60, or about 12%. Lots of different ones, right? We could look at that for each one of the colors. So we could create like a proportions test, hypothesis test for each of the proportions. But that would be, I'm sure you could imagine, very inefficient and time consuming to look at all 6 of those. And then it brings up other concerns and issues with statistics as well. So what we want to do is not look at the individual proportions for each of the 6 different category values. Instead, we want to look at the whole distribution at the same time and compare it to the distribution of counts we would expect, assuming the Mars company data. All right, so the null hypothesis is going to be that it kind of is the distribution of M&M colors is as the Mars company predicts it would be, or we expect it would be, assuming that the Mars company data is correct. And so then the alternative hypothesis would really just be that the distribution of colors is not correct based on the M&M company's data. So notice that the null and alternative hypotheses here are stated each as a sentence rather than using symbols like we used in previous chapters. Okay, so the null hypothesis is typically written with the, some kind of is correct, the data is correct, what we think it is true, that kind of thing. The alternative is going to be that it's just really the same sentence except they have the word not in it. Alternatively, we could write our null and alternative hypotheses with this kind of approach, listing the proportion from each of the 6 categories, but that's a little bit annoying and a little bit time-consuming as well. So we won't really do that. We'll use the approach on the last slide. Remember, too, that the chi-squared test is going to compare the observed counts with the expected count. So if we look at, we want to know how different the observed and expected counts are. So if the differences are really large, then that's going to be evidence against the null hypothesis. If the differences between the observed and expected are small, then that will be data that supports the null hypothesis. All right, so we can kind of just run through how to do these calculations. Again, we saw this in the last video. These are what we would expect based on the percentages that the company gave us. So these are the percentages that based on each color. We take each one of those and we multiply it by the sample size to get the expected counts. All right, so we want to compare those to the observed counts, and basically that's what the chi-squared test statistic is doing. It's comparing how different these 2 distributions are. All right, visually we could look at the differences from the observed and expected by comparing them in a side-by-side bar graph. So the chi-squared statistic endeavors to kind of take this visual and put it down as a value. It's like, how different are these 2 things? We eventually will want to get a p-value, and the p-value is basically saying how likely is it that we would get a difference as large as we did between the 2 distributions or larger just by chance alone. And so that sounds a lot like our p-value that we would calculate in previous significance tests. So that's where the chi-squared comes in. In order to answer that question, we have to calculate the chi-squared statistic. And you saw this formula. Remember, it's the observed minus the expected count for each of the categories. We're going to take each difference, we're going to square it and divide it by the expected, and we'll add those up over all the different categories. So to calculate it again, just to kind of visually see this again, in the M&M example, we had the blue, the orange, the green, the yellow, the brown, and the red. Each one of those contributes something to the final value of the chi-squared statistic. You can see if these numbers are, the contribution of the individual category is small, then you know that those two expected and observed values are pretty close together. When they is large, like the 3.8 here, that's when you'll see that the values are a little bigger than you would have expected. The difference is bigger than you would expect. Okay, so basically in a nutshell, we're looking for if we have a large chi-squared, that's strong evidence against the null hypothesis, and if we have small chi-squared statistic, that suggests that the data is supporting the null hypothesis. All right, so just like the t distribution, the chi-squared distribution changes based on the degrees of freedom. You can see the degrees in the curve here, the degree of freedom of 1 doesn't really have a hump. Degrees of 4 does have a hump, it's skewed strongly to the right. And degree 8 is a little less skewed. It looks a little bit more bell-shaped, and it's looking a little bit more symmetrical. And indeed, as the degrees of freedom increase, your chi-squared curve, distribution curve, will become more symmetrical and more normal. All right, the degrees of freedom, however, are not based on the sample size. The degrees of freedom are based on the number of categories, -1. So in the M&M example, we had 6 different color categories, and so our degrees of freedom would be 6 minus 1, or 5. Okay. Here is an example of a chi-squared table. We have this in the back of our books. We call it table C because that's the table in the back of our book. Even though we have a multitude of curves, it draws one generic curve for us to help us visualize that the p-value or the probability is to the right of our chi-squared under the distribution curve. All right, so in our example here, we have degrees of freedom of 5. Our test statistic we calculated before was 10.02. And that would give us the shaded blue region is our p-value. So we would go and look at row 5 of our chi-squared table. You're going to find that you will not probably have a 10.02 in the table, but just like on the t-table, we know that because it's between those two values of 9.24 and 11.07, that the p-value is between the p-values listed at the top of each column. So we know the p-value is between 0.05 and 0.1. It's still greater than 0.05, so we can still fail to reject the null hypothesis, even though we don't know a specific p-value. I would suggest looking, I put a link to this in the Google Classroom. I would suggest going online and looking at this website. It's nice because it changes the shape of the curve based on your degrees of freedom that you put in. Also notice that the shaded region is our p-value. Okay, so I would suggest clicking on that link and playing around with putting some values in, and it will calculate those values for you. All right, so some conditions we need to check before we do a chi-squared test for goodness of fit is the data has to be randomly selected or from a randomized experiment. Assuming we're doing a random sample and not an experiment, then we need to check our 10%, just like we would before. We cannot sample more than 10% of the population. And the large count here is looking at the expected counts, not the observed counts, but the expected counts. Make sure that when you're doing calculations, we're using observed and expected counts only. We're not using proportions. We're not using any kind of p-values or p-hats here, strictly using counts. And then a common mistake that people make is when you do your large count condition, people use observed rather than expected. You must use the expected values, not the observed values from the sample data. All right, so after we check our conditions, we can actually run the test. Remember, the null hypothesis is going to have something to do with correct, the word correct, or is as it's stated, something like that. The alternative is going to be that it is not correct. The null and alternative hypothesis are essentially stated exactly the same, except the alternative is going to have a not in it. Now, that's not true for every situation, but most of them will follow that kind of pattern. All right, remember that the chi-squared is using our counts, our observed minus our expected counts. We're going to square those. We're going to divide them by the expected value. And remember, then we will add those up based on each of the categories. Remember, there are k different categories, and so our degrees of freedom will be k minus 1. We do not use the sample size minus 1. So in our M&M example, we had 6 different colors. Our degrees of freedom are 6 minus 1, or 5. It is not 60 minus 1, so our degrees of freedom are not 59. The p-value that we're looking for is the area to the right of our calculated chi-squared statistic underneath that chi-squared distribution that we saw in the previous slides.